Let's move on to the third learning objective for Unit 1. This is where sorry, but it's memorization, but you should be able to identify the 7 essential elements for plant growth and identify whether it is a macro or a micronutrient. So this question is for the face-to-face class. And if you were taking this course face-to-face, I would say without cheating, and I would go up to the board, without cheating, how many can we list as a class? Now, you might want to pause this here and see if you can list this. Unfortunately, the list is also in your notes. So if you could do it without cheating, that's fine. Or you should understand the 17 essential elements for plant growth and identify whether or not they're macro or micronutrients based on the table in your notes. So let's move forward. What are the 3 most abundant elements in plants? Is it A, nitrogen, phosphorus, and potassium, B, carbon, hydrogen, oxygen, C, calcium, magnesium, and sulfur, or D, carbon, nitrogen, and oxygen? And if you were to choose, I would hope you would choose letter B, carbon, hydrogen, and oxygen. These are the most abundant elements within plants. And within the soil fertility realm, this is interesting because of what I'm going to share with you on the next slide and what's in your notes. So I broke the table that you have down in your notes into 2 sections. And this first section shows you the macronutrients, right? So the first 3 that are prevalent or dominate plants are hydrogen, oxygen, and carbon. And if you look at the amount, and if you skip the relative, let's don't focus on the relative concentration, but let's look at the average concentration. Carbon and oxygen make up about 90% of all plants. And this is true. If you were to quantify these concentrations within plants, you would get roughly 45 and 45%. Hydrogen comprises 6%. So 96% of any given plant is comprised of these 3 elements. And here's the kicker for soil fertility. Can we manipulate carbon to the extent where we can grow plants? We kind of do if you believe in climate change. I certainly believe in the amount of carbon dioxide increasing in the atmosphere, which contributes to this. But we're not doing this on purpose. I would hope we're not doing this on purpose. So can we, in soil fertility, manipulate carbon or carbon dioxide? We really can't. Hydrogen and oxygen come from water or the splitting of water. It's called hydrolysis. Can we, for the most part, manipulate the amount of water we apply to a crop? It depends, right? If you are in a rain-fed condition, like we are here in the Midwest, for the most part, right? There's always supplemental irrigation in locations. Or if you're in the Western United States where you're growing dryland winter wheat in Western Kansas, you don't have the ability to manipulate water to a great degree. And so the top 3 elements necessary for plant growth, we have relatively little control over. Okay. Then if you look at, well, let me take a step back. These are non-mineral elements. These do not come from the mineral phase within soils. They come from the atmosphere or precipitation or supplemental irrigation. So there's 3 primary macronutrients: nitrogen, potassium, and phosphorus. And within a plant, they comprise 1.5, 1, and 0.2% roughly, right? Still pretty high, but not as great as the non-mineral phases. And then there's 3 secondary macronutrients: calcium, magnesium, and sulfur. These 6 we can manipulate via fertilizers or amendments and their applications to soils. And we call these macronutrients because they're in great concentrations within the plants. And that's unlike micronutrients. So let me give you an example. Carbon is 45% on average within a plant. If you were to express that on a parts per million basis, that's 450,000 parts per million, right? So if you took 450,000 divided by a million, that would be 45% if you multiply that by 100. So keep that in mind for the next slide. So I place that value up here in the top right-hand corner. Carbon is 450,000 parts per million. It's a goofy way of saying or stating the amount of carbon in a plant. That's why the macronutrients we often express on a percentage basis. It's just simply easier. Now, let's take a look at the micronutrients. The average concentration of these micronutrients within plants is now expressed on a ppm or part per million basis. And we do this because it should make more sense when it rolls off your tongue that chloride and iron in a plant are on average 100 parts per million. If we were to express this on a percentage basis, it would be 0.01%, which just sounds goofy. And in fact, if you went down to molybdenum and nickel, which are necessary for plant growth, these values on a percentage basis are very, very small on a percentage basis. So it's more simple to express these on a part per million basis. And so the micronutrients that are necessary for plant growth are chloride, iron, boron, manganese, zinc, copper, molybdenum, and nickel. And then, so these have been found or shown to be necessary for all plants. There's 4 others that play roles in other types of plants or in agroecosystems or ecosystems. For example, sodium is necessary for sugar beets. Cobalt is actually necessary for rhizobia in legume nodules. Vanadium can replace molybdenum in green algae. And silicon is necessary for rice, cereals, and hemp production. And you should understand and know the 17 essential nutrients, and you could disregard the bottom 4, at least for this class.